Hello, everyone. Welcome to another ASEG technical talk brought to you by the ACT division. That's good. It's okay. I have the pleasure to introducing our speaker today.
You need to share. It's not sharing.
So welcome, everyone, to another ASEG Tech Talk brought to you by the ACT division. Today, I have the pleasure of introducing our guest speaker, Simon McClusky. Simon is the Senior GNSS Scientist in the Positioning Australia branch at Geoscience Australia. He had worked on the development of the GA's Ginan multi-GNSS positioning and navigation software project since 2020. Simon received his PhD from the University of New South Wales School of Surveying. In his early career, he worked as a research scientist in the geodesy and geodynamics group at MIT. In 2010, he returned to Australia and joined RSCS at ANU. Simon's early research has focused on improving the precision, accuracy, and usability of geodetic techniques, primarily the GPS for earth science research applications. And today we'll hear his talk on Australia's multi-GNSS positioning future. Before I start, the ASEG acknowledges the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We recognize their continuing connection to these lands, water, and culture, and pay our respect to their elders, past and present. We would like to thank our corporate members for their continuing support. And just for those of you who are not an ASEG member, I encourage you to become a member. You get free access to publications such as Exploration Geophysics, Preview Magazine, ASEG Newsletter, ASEG Special Publications, and ASEG External Abstracts from the ASEG and AEGC conferences from 2001 onwards. We have professional networking development opportunities. You get reduced registration fees to the Australian Exploration Geoscience Convention, access to the conferences and events hosted by the ASEG sister societies, short courses, technical events, and social events. We also have a huge range of online content, webinars, workshops, job advertisements, search for geophysicists and geophysical contractors to help you with your project, recognition for distinguished contributions and service to the profession through ASEG honors and awards. We have ongoing research and documentation of Australian exploration geophysics and geophysicists through ASEG's History Committee. We have a discounted membership rates for retirees and recent graduates. And we have an exclusive member discounted wines curated by the ASEG's SA and NT branches. So I think I have convinced you all to become a member, especially with that last one. So keep in touch. We have monthly newsletter updates. If you want to know about the events and what's happening, you can always go onto the ASEG website, aseg.org.au/events, and please follow us on social media. And with that, I hand over to Simon. Thank you.
Thanks for the invitation to come and talk to this meeting today. Yes, my name is Simon McClusky, and as Babak said, I'm the Senior GNSS Scientist here at GA in the Positioning Australia branch. We've done an acknowledgement of country, but I'll do another one again. So Geoscience Australia acknowledges the traditional owners and custodians of the country throughout Australia and acknowledges their continuing connection to the land, waters and community. We pay our respects to the people, the cultures and the elders past and present. So just to get started, I'm going to talk today about our multi-GNSS positioning future. But before I do that, I just wanted to say that the things I'm going to talk about today are only a small part of the things that we do in the Positioning Australia branch. So just as a bit of by way of a bit of an overview, so in the Positioning Australia branch, we are basically the national authority on geodesy and the verification of positions for geospatial applications in Australia. We operate a range of genetic infrastructure which enables us to provide services, geospatial services to the Australian geospatial community. We engage with other international stakeholders and geodesy communities on the data and standards that are used in the work that we do. We provide an analytic capability to process the data that's collected. And then finally, we deliver a range of precise positioning services and products that are used and are openly available to people who need to do precise positioning in Australia. And that's the last dot point is essentially what I'm going to talk about today. So I want to start by posing a question about how much you think you've used positioning, navigation and timing today in your life. So I think, well, a lot of people use P&T services on a regular basis. They don't really realise where those services come from. Things like for navigation through Google Maps, or if you're using Strava to track your running or swimming or riding. Your rideshare service uses GNSS P&T services as well. And then there are the range of traditional services like for surveying and construction and so on. So basically P&T is pretty ubiquitous in our everyday lives. And there are a few things here that aren't mentioned. This covers off on a lot of the positioning and navigation applications which you might use, but what a lot of people don't realise is that the timing that's delivered by GNSS satellites is also very important. Most of our financial systems and our energy grid is actually synchronised through GNSS timing. So that's also an important service which is provided by GNSS systems. So a few years back, GA undertook a study, or they actually commissioned a study to determine what the actual value of PNT was to Australia. So in the bottom line there, the report came back. It suggested over the next 30 years or so, the value of implementing a satellite delivered system for delivering more precise positioning called SouthPan would deliver benefits of around about $6.2 billion over that 30-year period. I'll talk more about SouthPan shortly, but it's a system that get about 10 centimetre positioning from a device which is able to track those SouthPan corrections. And then there was a further $500 million or so of benefit to be gained from the more precise service, which we call NPIC, the National Positioning Infrastructure Capability, which is a different correction service, which I'll also talk about a bit later in this service. There have been other surveys and reports done globally. In the US, they determined that they would be losing about the value of the GNSS system that they built, called GPS, has a value of about $1.4 trillion over its lifetime to date. And in another study in the UK, they determined if GPS and the other GNSS systems were to go offline for a day, they would be losing about $1 billion of economic value per day if GNSS was to be turned off or unavailable. So as you can see, it's quite valuable to have these GNSS systems available. So as I mentioned before, Australia is in the process of developing two new positioning services. One of them is this service called SouthPan, which uses a system of satellites to deliver corrections so that you can augment your basic GPS positioning capability to improve it from several metres down to 10 centimetres of accuracy. And as it says there, the corrections are delivered either via a geostationary satellite that's tracked by your handheld device, or they can also be delivered by the internet. So you can get those corrections through a mobile internet connection as well. And the second system we're working on, which is called the National Positioning Infrastructure Capability, that's capable of delivering 3 to 5 centimetres of positioning accuracy, but only in areas where you have a mobile internet connection, which is depicted in that map there. So you can see Southpan delivers corrections for the whole continent, but at a lower accuracy, whereas the NPIC capability delivers a more precise service, but with lower spatial coverage. So I've introduced a little bit about what Southpan is. So Southpan is the Southern Positioning Augmentation Network. It is basically a system that relies on a geostationary satellite to deliver the corrections to devices on the ground. Early open services of the Southpan system started in Australia it was a couple of years back, probably in 2022 or 2023. And when it's finally completed, it will have a safety of life service available, and that's expected to be rolled out from about 2028 onwards. As I said before, the estimated economic benefit of Southpan is estimated to be on the order of 6 billion over the 30-year lifespan of the system. The other service, which I've talked about, the National Positioning Infrastructure Capability, is essentially a unified approach to the management of our nation's positioning infrastructure. That's both the physical infrastructure as well as the software that's used to access the data and produce precise positioning. At the moment, the ground stations, the physical infrastructure of NPIC, there are about 700 stations, and they're openly accessible to anyone who wants to have access to those data. I won't go into any details, but this is just a summary of some of the areas that were identified in the report where there would be economic value to be gained by improving Australia's real-time precise positioning capability. They basically range across areas from agriculture to mining to ports, as well as the road system through smart transport systems. The one in the bottom corner is from having better timing systems, fewer blackouts potentially. So yeah, there was a range of things identified across about 45 applications and 10 industry sectors that would be benefited by having this improved precise positioning capability. Just quickly looking at what Southpan is going to provide. So these are the coverage areas that Southpan is currently envisaging providing services over. In fact, where they are providing services over. So the early services of Southpan are already operational. So in the light blue area that's shaded is where you get the open L1 only positioning capability. So that covers most of the continental Australia as well as New Zealand. And the dual channel, the dual frequency multi-channel service, which uses 2 GNSS frequencies instead of 1, is available in the hashed area. So it's over a slightly larger area than the L1 only traditional SBAS positioning capability. This is just a summary of the services that are currently available from Positioning Australia for precise positioning at this time. So I'll come back to some of these a little bit later when I talk more about what Ginan is and how it's different than traditional positioning systems. So the top one is a single base station RTK service provided by the base station network, which we've developed across the country. There's the L1 SBAS service, which I've talked about on the previous slide. There's the dual frequency multi-channel SBAS service, which has the slightly larger service area. There's this thing called PPP via Southpan, which is essentially a precise point positioning service, which gives you a little bit better accuracy than the dual frequency multi-channel, but it's got some disadvantages with convergence time or how long it takes you to get that better positioning capability. So all of those services are available via the satellite connection, but they're also available over the internet, which is the next 3 that are listed. And then finally at the bottom, there is this idea of providing corrections from Ginan in a format called a states-based representation, which I'll talk a bit more about later on as well. So that's basically a summary of the suite of positioning options that Geoscience Australia is providing at this time. A little bit on the infrastructure used. So the SBAS space segment, as I've mentioned, involves a geostationary satellite, which receives the uploaded corrections from ground stations and then rebroadcasts them back to Earth across the Australian region for users to receive in their handheld devices. There's a ground station. There is a ground segment to the SBAS system, which includes a set of continuous operating reference stations or GNSS stations, which basically bring in data, calculate the corrections, and then those are rebroadcast through the geostationary satellite back to the users to improve their positioning. So that's the ground segment, and then the user segment is the receivers that you have in your hand. So that's the GNSS receivers, which not only track the GPS or the other GNSS satellites that are available, but they also track this geostationary satellite, which is broadcasting on its own L-band channel called PRM 122. And that's how the corrections are delivered to the user via the space segment. And as I said on the previous slide, there's also those corrections are available via the internet through a protocol called SysNet. So as part of building the SBAS system, the SBAS team has had to roll out a new set of reference stations that are highly redundant, so that the data is always available for calculating the corrections. They've had to negotiate land acquisition to put these reference stations on. They've had to build 2 uplink facilities, one in Urella in Australia and the other one in New Zealand. And they've also had to build a centre processing facilities to actually handle the data coming in from the cores networks and then to broadcast them to the geostationary satellite. This is just a map which shows where the current infrastructure is, or where it's planned to be rolled out for the southbound network. You can see that in the red diamonds, they're the 2 upload stations for the corrections that are being broadcast, and then the blue triangles are the locations of the ground stations that are used to collect data for calculating the corrections. That was Southpan in a very quick summary. Most of this talk I will be concentrating on the part of the system that I've worked on, which is the National Positioning Infrastructure Capability. And this consists of a couple of parts. Again, there's a ground network of GNSS receivers on the ground, which collect data continuously. They transmit that to a data center where it's archived and also made available to users to use in real time for positioning. And then we have this Ginan processing center, which allows us to take the data from the cores network, process it, calculate corrections similar to the corrections that are produced for Southpan, and then make it available through the data center to users to be able to position themselves with 3 to 5 centimetre accuracy anywhere where they have an internet connection. This was the value proposition for why the National Positioning Infrastructure Capability was created, or why it was improved over time. It basically underpins Australia's geospatial fabric. It allows us to define a datum for mapping in Australia, which is accurate. It supports research and encourages innovation through the delivery of free and open data and services and positioning services. And it provides a platform for Australian businesses to be able to innovate using those data and services by providing services to the community. These are the things which the NPIC capability has to deliver. We're delivering a unified network of infrastructure. That's essentially the ground stations which have been rolled out. And I'll show you what that looks like in a second. We've improved the way that the products and services are delivered to the community for use through this thing called the AusCores platform, which is essentially a web service that allows people to access the data, both the files and the streams in real time. And then thirdly, we're also developing this toolkit that enables people to actually use those streams and data to either do post-process precise positioning or to do real-time positioning. And we'll talk much more about that in a minute. This is a map of the current physical infrastructure, which has been rolled out in Australia as part of the NPIC build-out. So 5 years ago, the network was around 100 stations and largely confined to the southeast of Australia, as well as the southwest corner of Western Australia. Since then, a lot of stations have been rolled out in really hard to get to places, which has been a challenge. But today, this network is essentially operational across all of Australia. This is what a typical GNSS ground station looks like, a reference station. So on the right-hand side, you can see there's a box, a green box, which contains the receiver that's tracking the GNSS satellites. There's also redundant batteries in there, and there's a solar system to charge that battery. There's also a communication system in there as well, which enables the data to be broadcast in real time back to the Geoscience Australia data centre, where it's rebroadcast or archived. And on the right is the monument or the pillar on which the antenna, so that's actually the reference point to which the station refers to. And on top of that pillar, there's actually an antenna which is connected to the receiver for tracking the GNSS satellites. So it's the precise position of the top of that pillar, which is the reference point in this system for this station. As well as installing our own infrastructure, Geoscience Australia has also licensed data from a number of third-party operators of GNSS infrastructure. So on the bottom left there, you see some of the other operators of GNSS infrastructure in Australia who GA has negotiated licensing agreements with. And that brings the total of GNSS stations available through NPIC from the 200 that we've operated and installed, plus these 500 brings the total to around 700, which are available for users to get data from. The data that's collected and broadcast to the users is done through this thing called an NTRIP broadcaster. So NTRIP is just basically an HTTP web service. It's a way of packaging up GNSS data into chunks and then making it available in real time to users through this thing called an NTRIP broadcaster. It's basically a bunch of acronyms within an acronym. So I've put them down the bottom, what NTRIP stands for. It's the Network Transport of RTCM via Internet Protocol. You'll notice that there's an acronym within the acronym, so then you have to read what RTCM stands for, which is the Radio Technical Commission of Maritime Services. So, and that's basically the organisation which defines all of the standards by which GNSS or positioning data is broadcast via the internet. Then RTK, which I'll talk about a little bit later, is called real-time kinematic positioning. That's that acronym as well. So yeah, there's a lot of acronyms, I guess, in most of these fields. It's very similar to you. So anyone, as I said, the data is freely available to anyone who wants to connect. You have to register to get a free account to the AusCores server. Once you've registered, then you can connect to these real-time streams for either positioning services for RTK or for using Ginan through a set of SSR corrections. So that's basically the summary slide for the network infrastructure, 700 base stations, broadcast continuously. And as I said, there are 10 streams of SSR corrections which can be used by Ginan as well. As of late 2023, the availability of the AusCores service was about 99%, 99.9%, so very reliable. Now I want to talk a little bit about Ginan, which is the software capability that we're building to be able to process this data and analyse its quality. So I just wanted to touch on a little bit on where the name Ginan came from, in case you were wondering. So Ginan is a First Nations word from the Waterman people in the Northern Territory. The word means a red dilly bag filled with songs and knowledge. And since Ginan is a software suite for doing various things with GNSS data, we thought that would be a relatively good analogy, that you keep things in Ginan that you can use for helping you do navigation or navigation-related activities. And Ginan is also the word which has been used by the International Astronomical Union for the 5th star. It's been given to the 5th star, the smallest star in the Southern Cross, and that sort of has a navigation feel to it as well, because the Southern Cross gives you an ability to navigate, or north and south is at least. So it kind of covers off on the idea of it being a suite of tools for gaining knowledge about navigation. This is a bit of a busy slide, and I won't spend too much time on it, but we looked around when we were starting to develop Ginan for all the potential use cases, and we found there were plenty. There were some we found in academia for doing research and addressing research questions. There were things that we wanted to do as in GA for geoscience purposes. There were a range of things that government wanted to do as well. And then there were finally some industrial applications. So there were a whole range of things that that Ginan can be used to do in various sectors of the economy, which again was one of the motivations for actually starting to develop the software in the first place. So now I'm just going to talk a little bit about what exactly Ginan is. So this is where it starts to get a little bit more technical. So that little picture on the right-hand side is a satellite visibility map, a GNSS satellite visibility map. So the redder colours, the hotter colours, are where if you were standing on the ground, you could see, and you looked up, you would be able to see more GNSS satellites. And then the lighter colour, or the bluer or greener colours, are where you can see fewer. And you can't see the outlines of the countries too clearly, but in the southeast corner of that red blob is where Australia is. So what you can see is that Australia, once all of the GNSS satellite systems are fully operational, which they are at the moment, if you look up, you can see on the order of 35 to 40 satellites visible at any one time. And traditionally, most analysis software for GNSS navigation purposes used GPS only data. So that's the US system of providing navigation services. Since GPS, there's been systems launched by the Russians called GLONASS. The Europeans have launched a system called Galileo, and then the Chinese have launched a system called Beidou, and then Japanese have a regional system called QZSS. I can't remember what QZSS stands for. So anyway, there are 5 other systems, or 5 systems now, which enable you to do positioning on top of doing GPS. So what we wanted to do was make sure that we exploited Australia's position under these GNSS services for doing positioning. It turns out that the more satellites you can see simultaneously, the faster you can converge to a precise position than if you just have fewer satellites. So that was one of the main reasons for doing it. We wanted to develop a system that didn't require differencing of the data, which I'll come back to in the next slide. We wanted something that was scalable and could operate in a network mode for generating the corrections that we would broadcast to users, as well as ingest the corrections to enable the users to do their positioning. So it does both the creation of corrections and the use of those corrections for user navigation and positioning. The software uses a Kalman filter as its optimization algorithm. So it supports real-time and post-processed data applications. It supports the ability to do positioning of static objects like a cause station, where you want to know the coordinates very precisely, and it also supports the positioning of kinematic objects. That's things that are moving, like cars or planes, drones, boats, whatever. So it positions in both those modes. It uses all of the industry standard file systems, or most of the industry standard file systems, and streamed-based formats. It also integrates a precise orbit determination capability, not just of GNSS satellites, but also of other low Earth orbiting satellites that are carrying a GNSS receiver. It includes tools for doing quality assurance and of data from GNSS stations. So if you wanted to monitor one of your stations, you could use Ginan for doing that. As I mentioned, it does low Earth orbit estimation. It also can take data from this other geodetic system called satellite laser ranging, which is a system where you shoot a satellite with lasers and you look at how long the pulses take to go from the ground to the satellite and back, and from that data you can also determine the orbit of those satellites. So it's also able to process that sort of data, not just the microwave GNSS data. And it's an open source toolkit, which means you don't have to pay to use it. You just have to go to GitHub and download it, and it's available for commercial, scientific, research, government sectors, for anyone who wants to use it. So this slide is now getting into what Ginan is, which is a PPP, precise point positioning software, relative to a more traditional RTK positioning software, which MPIC supports both SSR or PPP and RTK positioning. What I'll talk about shortly is why PPP is useful on top of having the RTK capability as well. So this equation here is basically the observation equation for GNSS observations. So on the left-hand side, P is the range that your satellite, from the user to the satellite, and that range is made up of the geometric range between the satellite and the ground station, and then a whole bunch of other things which change that range. So you've got errors caused by the clocks on the satellite and on the ground station. You've got errors caused by the troposphere as the signal propagates. You've got errors caused by the ionosphere as it propagates. You've got biases in all the equipment at either ends, and then the O is the orbit errors, and then you've got random noise at the end. So when you're doing GNSS positioning, as you improve your knowledge or remove those biases, you get more precise positioning. So that's essentially what we're trying to do with both of these techniques, is to actually find some way of removing these unknowns or these biases which are affecting the range, so that we can do better positioning. So in traditional RTK processing, what you would do is you would basically calculate your relative position between the base station and the rover on this picture on the right. And by taking the data from both ends, from the rover and the reference station, and by differencing them, all of the things which are unknown between those two observations, which are common, when you difference them, those things disappear. They difference away. So you're just left with the geometric range, some ionospheric errors, and everything else is gone. So that's why RTK positioning, which was the original way which surveyors did differential positioning, was invented, was because it's an easy way of getting quite precise positioning using observations from two ends of a baseline. So this ionospheric component is removed by using two frequencies. The ionosphere is dispersive, so if you observe with two frequencies that are propagating through the ionosphere, you can combine them in a way, in a linearly combined way, in which the ionosphere is actually removed from that observation. So by observing on two frequencies, that's how we can remove the ionosphere. So in RTK, you can actually get rid of all of those things just by differencing and using a linear combination, ionosphere-free linear combination of the data. The only downside of this is that, as is indicated at the bottom there, it only works for short baselines. So long as your rover is within about 30 kilometres or so of your base station, this method works quite well. You can do centimetre level positioning. Once you get outside of that distance, these errors, particularly the troposphere, doesn't cancel out anymore. So you can't just difference it away, because the troposphere in Sydney is way different than the troposphere in Canberra. So that contamination doesn't difference away any longer. So it doesn't actually work. So for those longer baselines, we need another technique, and that's where the PPP comes in. So for PPP, instead of relying on differencing of observations, what we do is we bring all the data from the large Australian network of GNSS receivers into the software, and we actually estimate all of those things. They're called states in the Kalman filter. So what we do is we estimate an estimate of what the troposphere looks like, what all the biases look like, what the clock errors look like, and then we package all those corrections up into an RTCM message format, and we broadcast them over Ntrip, and then the users can then, on the other end, they can read those corrections, and then they can correct for all of those things. So instead of differencing away the errors, they actually plug those numbers into the equation at their end, and then calculate a precise range based on those corrections. So that's where the state space representation comes from, the SSR, versus for RTK, the OSR is the observation state representation. One, you're differencing observations, and the other, you're actually applying corrections which have been pre-calculated for you. So that's essentially the two different ways of positioning that we currently make available. RTK is very good, as I say, for short baselines where you need precise positioning, but if you're very far away from a base station, you'll need to go to the PPP methodology. A little bit on timeline. So we've had 3 releases of Ginan to date. The first was a fairly rudimentary version in July 22. We went to the undifferenced uncombined methodology in July 23, and then earlier this year we released a version of the software which had modelling for the ionosphere and troposphere models that we could broadcast to users, as well as a few other things like this capability of estimating low Earth orbiting satellites orbits as well. And at this point in time, we're essentially just doing, we're still resolving a few issues in generating some of the products, not around the how we do it, it's more around how quickly we can do it. So we're trying to improve the performance of the software to make it quicker to run in our operations center. Won't spend too much time on this because I think it's going into a little bit too much detail, but these are the major parts or the major modules that exist inside the software suite. So there's a file which enables you to configure Ginan to do what you want, if it's to generate corrections or to receive them and process them. You specify in the data input section what data you would like to process. Is it some files that you have recorded, or if you wanted to connect it to some real-time streams that are coming in, you do that through the data input section. There's the modelling and prediction part, which we've just talked about. We have to build that model with all those components in it. Then there's the Kalman filter, which actually does the optimization and the estimation of the states. We have to do some error checking in the filter. So there's an error handling segment. There's this thing called augmentation, which allows us to handle the output in different ways. So we can decide, do we want to output an ionosphere model? Do we want to output positioning products? So that's what the augmentation part does. And then finally, there's the output module, which basically either sends the service, the products to a file, or broadcasts them out as a stream on the Ntrip caster. And then we have some back-end scripts and visualization tools for looking at what the software's done as it's processed the data. So just getting on to some results now. So what we're looking at here are some results of using Ginan to do precise point positioning of static sites. So these are basically, we've computed corrections, we've stored them in a file, then we've got the data from the base station, and then we've processed it using those products, those positioning products. And what you can see on the left-hand side is if we produce the products at a 5-minute interval, so every 5 minutes we produce a set of orbits and clocks, and then we process the data that's coming in from the base station every 30 seconds with that 5-minute late or that 5-minute interval product suite. You can see that we're getting these are the numbers to look at up here. So this is the standard deviation is the root mean squared difference between the position that Ginan's getting and what we know the known position of that is from previous analysis of that station. And you can see the standard deviation using these 5-minute products is around about 7, 5 and 0.1 metres in the northeast and up components. And the main reason that hasn't met the 3 to 5 centimetre standard that we were hoping to reach is because the products that we're providing is 5-minute interval. Over here, we process that same data, but now instead of providing the products at 5 minutes, we're now computing them and providing them at 30 seconds. You can see that the standard deviation now has come down to about 1 centimetre in the two horizontal components and about 3 centimetres in the vertical component. So that is below the threshold that we need for meeting our 3 to 5 centimetre positioning standard in the Ginan software and products. So yeah, it makes a difference, and gets back to what I was saying before. We're trying to improve our capability to provide the products in a more timely way. So we'd like to actually provide the products at less than 30 seconds, because there are applications out there, like when you're moving fast in a car, for instance, you don't want to wait 30 seconds for your next update. You'd like to be able to get it the next second. So our aim is to try and get that number down as small as possible so we can provide. It's mostly the clocks which are not predictable. So the atomic clocks that are on the satellites, they have quite good long-term stability, but their short-term stability is not that good. So over 30 seconds, you might have decimeters of noise in that clock, whereas over 1 million years, it might only lose a couple of seconds of time. So it's the short-term versus the long-term stability of the clocks that you have to worry about. And this is just another example of some results that we've got. So this is now, in the previous slide, we were looking at kinematic positioning, where we assumed that every time we process some data, we just assume that that station can be anywhere. It's not correlated with its previous position. In this static positioning, what we're doing is we're estimating the position of a station based on a whole series of data. In this case, it's a whole day of data. So when we assume that the station's not moving, like a core station, and use all the data from that day, 30 seconds of data, we're going to get standard deviations which are way below the sub-centimetre level. So at the millimetre positioning capability, when we assume the station's not moving and use the products that we are able to derive from the network. And then the plot on the right is basically how fast do we get to a certain precision. So this dotted line is our 5 centimetre threshold for positioning. So, and this on the x-axis is time. So how long does it take us to get below the 5 centimetre threshold for our position? It's usually on the order of, this is the GPS only processing, so it's usually on the order of about 30 minutes or so, 30 minutes or less. If you add in the other GNSS systems, the Galileo, GLONASS, Beidou, you can get that down, that converges below 5 centimetres down to a few minutes, certainly less than 10 minutes. I won't spend too much time on this either. This is basically talking about Ginan's orbit estimation capability. Initially, when we first built the software, it had a separate orbit determination module to the optimization module, the Kalman filter. We found this was a bit cumbersome to operate. So what we've done now is move the orbit estimation capability within the Kalman filter. So every time when we're estimating orbits, the Kalman filter steps forward with new data, we're actually running the orbit integrator to get the satellite's predicted positions in real time without having to step out to another piece of software and then re-inject them again. So this was just a thing that we did to make the Ginan to be more useful for doing real-time orbit estimation as opposed to post-processed orbit estimation. We've done a lot of validation of the orbit modelling that Ginan has in it. So these are all of the things that Ginan takes into account when it's trying to figure out where the satellite's going to be, given where we know where it is now. So all of these different tides and forces, solar radiation pressure, Earth albedo force, there's a whole bunch of them. And it's probably the most complicated part of the whole software. But and the accelerations that these things are imparting on the satellite are on the order of nanometers per second squared or less. So we've done a lot of validation against other orbit integrators from various institutions around the world. And the red lines are where Ginan sits in terms of its difference to one reference piece of software. And then the other symbols are for where other software sit in that comparison. So we're fairly confident that our orbit integrator is relatively precise or accurate at this point. This is just another example of using Ginan now, not in single point positioning mode, but this is in the mode where we're actually estimating the products for positioning. So in this example, we've taken the data from that global station of nearly 100 stations. We've processed it in Ginan for a day, and we've estimated what are the positions of the stations. So what are the positions, the XYZ positions of all the stations? What are the positions of the satellite orbits? What are the values of the clocks on the satellites themselves? So in the graph on the right, it's showing you what our estimates, the difference, or the RMS, or the standard deviation of our estimates relative to what's considered the known values of those stations from a very long period of tracking them, processing the data with other software. So in the horizontal components, which are the two left ones, we agree within 2 to 4 millimetres, and in the vertical, in the up, we agree with in less than a centimetre relative to these standard solutions. This plot here shows you how our orbits differ relative to orbits generated by other processing centres. And you're looking at the differences in the radial direction, so where the satellite is radially from the Earth. The transverse direction is a long track, where the satellite's moving, and the normal is across the plane of the orbit. So that's the root mean square, or the RMS, relative to the best reference orbit we have. So in the radial direction, it's about 1.5 centimetres. In the long track direction of the satellite's moving, it's about 2.5 centimetres, and in cross track, it's a little bit less than 2 centimetres. So those are the accuracies at which we're positioning satellites that are about 26,500 kilometres above the Earth, travelling at about 3.5 kilometres a second. And again, that's based on an average of 24 hours of convergence before we start comparing the orbits and clocks. And this is the difference between our best satellite clock values versus the reference clock that's generated by the International GNSS service. So you can see our clocks, each one of these lines is a different satellite, and our clocks on average have an RMS difference from the reference standard of around 2 centimetres, which is about 63 picoseconds in time relative to the standard. So these accuracies are about as good as what other analysis centres are doing. They're maybe not quite as good yet, but they're certainly getting down to the point where we would be able to submit these solutions to the GNSS service for actual inclusion in that combination. Just some other things that we've done. I mentioned that we introduced low Earth orbiting satellite positioning capability. So if we take data for an orbiting satellite, in this case, it's one of the GRACE satellites, which is used to recover the gravity field of the Earth. It also has a GNSS receiver on it. We take data from that satellite and we compute its orbit. This is 3D difference from JPL's reference orbit for that satellite. So JPL has their own software for doing, that's the Jet Propulsion Laboratory in Pasadena. They have their own software for generating satellite orbits. If we treat the satellite as completely kinematic, that is each epoch, we don't know where it is relative to the previous epoch, we get around 5 centimetres, 7 centimetres of difference from the reference orbit. If we use the orbit integrator and we use it to predict where the satellite's going to be at the next epoch, and then we also introduce the data as well, so we kind of do a weighted average of the prediction of our model prediction and what the data says, we can get down to within a centimetre or two of where the reference orbit says the satellite would be. And then the bottom of the graph is just a time series of those differences between our orbit and the reference orbit for one day. You can see there within a couple of centimetres or so. In the interest of time, I'll skip over that one. Another thing that we're doing continuously now is we basically have an operations centre set up where we're monitoring the location of some of the core stations that GA operates, just for quality assurance. So basically we're taking in a stream of data, processing it with our SSR products, and then plotting on a graph or in a time series where the station is relative where it should be. And that tells you something about what the quality of your positioning products is. And it also, if someone is nearby and they're trying to corrupt your GNSS station, if suddenly the station looks like it's somewhere else or goes offline, this monitoring system is a way of determining whether someone's trying to mess with your your GNSS positioning capability. So that's something we're developing at the moment, is this ability to monitor what's actually going on in the network that we're using to produce these corrections. Something else we've done is, because we wanted to be able to create a system that other people could take and innovate on, what we did was we got a team at Frontier SI to build us what we call Ginan in the box. So we got them to take a Raspberry Pi, a little computer, stack on top of it a GNSS receiver which can track satellites, and then on top put a battery. And then they installed the Ginan processing software on the Raspberry Pi. They connected an antenna to the GNSS receiver, and then they used it in various applications for doing positioning. So they took it up to the Ames Research Centre in Townsville, and they stuck it on these things that they use for monitoring the reef, a surf bee. They put it on one of their drones, fly it around, and then in another demonstrator, we also put it on a weather balloon and sent it up to 30 kilometres in altitude to see if it would operate at those heights. And the aim here was, again, just firstly to test that Ginan could be deployed into a small computer like a Raspberry Pi and used for positioning, and also just to see what the quality of the Ginan positioning would be like in a situation like this. So this is on the right-hand side. You see the picture of where some of the data they collected up in the Ames Research Centre was. The purple dots are where they flew the drone around, and the blue is when the surf bee was parked by the dock for a period of time. When they actually, this is the picture of the surf bee here with the antenna. Ginan in a box is in this case, which they've got stuck on top of it. And then when they compared Ginan to the results that they got from an RTK positioning system, which is the one, because they had a very nearby base station which they could do precise positioning to here. So the Mosaic RTK is the precise positioning results, and then Ginan PPP are the values that are associated with the Ginan ones here. And as you can see, Mosaic RTK is much more precise because it's a very short baseline, just of a few kilometres. But the Ginan PPP generated results which were within our 3 to 5 centimetre positioning envelope, which this was done quite a while ago now, where our PPP SSR corrections weren't as reliable as they are now. So probably if we repeated this, we'd probably get even better results at this point. As I mentioned, the other thing we did was we were interested in whether Ginan might be able to use for things like positioning weather balloons more accurately, or getting profiles of the water vapour in the troposphere. Because one of the things, as you saw from that equation that I showed earlier, is that one of the things that's recovered when you process GNSS data is the estimate of the tropospheric delay. And that tropospheric delay tells you something mostly about how much water vapour there is in the atmosphere, because that's one of the main components of that delay. So we decided we'd get the BOM to put Ginan in a box under one of their ionospheric sounding weather balloons, and then launch it in Melbourne. And this is kind of a picture of them putting it out, and then you've got a track of where it went up. So you can see it basically applied this far up, went into this, back down again. And from that, we were able to retrieve a precise altitude map. So the red line is showing you the altitude of the balloon, followed way up and way down. And the blue line is the estimate of the tropospheric delay, how much delay was by the wet part of the troposphere. So you can see when it's at sea level before it's launched, it's about 2.5 metres. The tropospheric delay, as it rises up through the atmosphere up to 30 kilometres, that number goes down to essentially 0. So it's telling you that there's no water vapour above 30 kilometres in the atmosphere, which is pretty much what we expected. This experiment. So that's pretty much all I have. It's a pretty quick overview and introduction to what Positioning Australia is doing, both with South Pan as well as with Ginan and the NPIC program. As I said, the software is open source, so you can go to our GitHub site and download it. We provide it in various different ways. You can take the source code and build it yourself, or you can get a Docker image, which has the software already built in it. There's also an app image the software as well, which you can run on a Windows system. Yeah, I think that's pretty much it at this point. So I'm happy to take questions if anyone has them.
Simon, about the clock, estimated clock from the Ginan. So I believe it's precise enough. So will it become the clock or the time standard to support the national time standard in the mind? So
No, I don't think so. I think that they'll rely on their own atomic clocks for that purpose. Ginan would be useful if you had the time at one of those places like NMI from an atomic clock there, and you wanted to synchronize a clock somewhere else to that time standard, then Ginan would enable you to do that with an accuracy of around about. In fact, I was working on this today with an accuracy of around about 20 picoseconds is what you could actually transfer time between one frequency source and another. But GNSS doesn't keep, the system itself doesn't keep accurate absolute time. That relies on ground. So the system that the satellites keep, the time that's on the satellites, is determined by a set of ground stations, which is run by, in the GPS case, it's run by the Department of Defence. They have their own suite of atomic clocks on the ground. Don't know where they are. I guess that's secret. But they use those to calculate what the clocks are on the satellites, absolutely, with respect to their time standard. And then when we use Ginan, all we're doing is connecting our time standard to what the time standard those satellites are keeping. So yeah, we can't do very much about keeping absolute time with Ginan, but we can transfer it very precisely between one place and another using the software.
You showed a map of all the locations that are operated by Geoscience Australia. I think there were 200 of them across the country. So, I mean, this is maybe not directly related to your talk, but what's the arrangement between GA and those landlords where the stations are? Are you linking those
I
landlords?
think that was one of that's the hardest thing to do in all of this, in rolling out a network like this. It's not the building of the site or getting the communication system set up. It's actually negotiating the land access rights. So that was done by the team a few years ago, and I know there was quite a few people that worked on that, and I know that it was quite, as you know, from the seismology field, getting access to pieces of land to put your instruments on is very difficult. And yeah, so that was a very large part of the work that had to be done, was just finding places where you could actually put the receivers with permission.
Okay, do you want to read it? No, good.
I asked, how can Ginan supply precision GNSS data, particularly for tracking ground movements, be integrated into seismic monitoring networks to improve early warning systems or post-seismic displacement studies?
That's a really good question, and that's one of the reasons that I came from ANU to here to help build this system, because I'm very interested in seismic hazard. And if we can make the system work precisely enough in real time, then we can actually track at 1 Hertz rate the deformation of the Earth in real time at millimetre precision. That's the aim. And our colleagues in New Zealand are very interested in whether they might be able to use Ginan for exactly that purpose, for doing real-time seismic hazard alerting.
I am very interested in that too.
Yeah, that's definitely an application which we're very interested in pursuing in the future.
Can I ask a question?
So, following this question, so will Ginan be with the PPP RTK function in future, or?
Yeah, so right now, so Carl's asking something I didn't actually cover. So PPP has a number of different grades of quality associated with it. So standard PPP is you just provide the orbits and clocks to the user and some biases, and they can do more precise positioning. There's another where you provide the ionosphere estimate, an estimate of the ionosphere across a region to the user. And with that, they can do ambiguity resolution, which lets them get faster convergence of their positioning. And then the third upgrade to that is called PPP RTK, where you're providing clocks, orbits, biases, ionosphere, and the troposphere, a model of the troposphere over the user as well. And essentially at that point, you're doing positioning just like you would do with RTK, short baseline RTK positioning. But so far, we have the software has built in the ability to do an RTK PPP solution, but we haven't got the processing figured out yet as to how we can get all the data in, all the corrections calculated, the models estimated, packaged up into messages and sent to the user yet. So that's part of this performance issue that we're still working on, is how do we actually get all this done in the few seconds that we have from when the data is collected to when the user needs to get it. So yeah, that's part of the work that we're still working on, is operationalizing the software that we've already built to do this. Sure, it can do it, but it takes 3 times longer than it needs to do it. So we're trying to optimize the software to do the things that we want to do in terms of RTK, PPP positioning.
Yeah, Sima, your hands are up. Your hands.
Oh, yes, it is on. Simon, thank you so much for your presentation. I learned a lot, like as a non-expert in this area. I have a question after seismic hazard one. So about GNSS stations, how do you pick the location of installation? I think there is more bias toward East Australia rather than West. Am I right?
Yeah, so at the moment, people put them in places where they think that somebody's going to use them. So that's why you'll notice all the GA installed stations are in places where there aren't people, because we needed a network which covered the whole country so that we could produce ionosphere and troposphere models for everywhere. Whereas all of the third-party providers are all concentrating around Southeast Australia, where the population is, where there are surveyors who want to use this RTK technique for doing positioning. So that's why the GA network is much more evenly distributed, and the third-party service providers of RTK services are all clustered in populated places.
Yeah, thank you.
There are some use cases in non-populated areas.
Mm-hmm.
On cave, go and look for new cave sites out on the Nullarbor.
Yeah.
And so there's not, didn't used to be fantastic GPS reception even out there.
Right. Yeah.
So,
So I think Southpan will definitely be helpful in that situation, because I presume you don't have internet coverage out there either. So
no, only
Ginan
coming
is
from
gonna
the highway and the
yeah.
roadway.
But Southpan will provide you 10-centimetre-ish positioning anywhere. So that would certainly be helpful if you need better than metre level positioning for those things.
Great to see how the developments are going.
Sure, there are probably some junior exploration companies who are looking for more precise geophysical positioning capabilities, which I think Southpan will certainly provide them fairly easily in the future. One for each hand. No, we'll get a picture.
Yes. Picture. I should stop the feeling.
You want me to hold the mic?